Okay, so this is the beginning and the end of the series of talks, introduction to sandpiles near the tropical limit, in particular the tropical sandpile model. And today we are facing the overview, which is not supposed to be an introduction and so on. So, like, I'm assuming a lot of things from the listeners. So, some basics of tropical geometry, and in the first talks, I'll explain some of the sandpiles. But I decided that instead of doing the top links and so on, just straight on go to the example. And so this is an example of what happens if you start with 9 by 9 board with all threes except for one point where you have four. And then moving from left to right, you do top links. So first, there is only one top link to do. You do one top link where you have four. And then you have four more squares where you have less, greater than four, greater than three, like you have four, where you can do the top links, and then you do this top link for top links. You have the next picture where you have 6 places to do the top links, and it goes for quite some steps. So I don't know how much, but this is an example of a relaxation. And in general, we are interested in solving what is the result of the relaxation for this kind of situations, where you have a board with almost everywhere all three, except for a few points, maybe one, maybe two, maybe some number n, where you have four. So this is the setup of the problem. And the general strategy for attempting this uh, uh, yeah, for attempting this relaxation, solving this relaxation is through decomposing it into waves. And the waves, as I promised, I'll insert some references. We were introduced in 1994 by Ivashkevich, Ktitarev, and Prijev. I think it's Prijev. And yeah, we thought that we invented them, but actually it was 20 years before us. So anyway, so that's an example of a wave propagation. So to do a wave, you force a top link. So you had a board with all threes, and where you have now -1 on the left upper corner, there you did the forced top link, meaning that you reduced the 3 by 4, having -1, and you give 1 to each of the neighbors, and which results in 4. And then you do the usual relaxation. So when you pass to the right, you do 4 top links, then you do how many 8 top links, and etc. So you do quite some number of steps, but here the pattern is clear. So if you look at these pictures, you see that the result is going to be ones in the corners of the square and twos along the boundary, which is not the square. And that's the result of applying a single wave. And the general statement that we are not proving, but in these talks, but which is kind of straightforward, is that any relaxation of a state that I mentioned can be decomposed into a sequence of waves, and adding the point at the end. So that's the subject of the first talk, relaxations and waves, where I explain how you define it all, these relaxations, if your lattice, if your graph is the whole lattice, for example, or some infinite graph, and we define the waves. So that's for your information how the result of applying several waves would look like on the same graph, on the same 9 by 9 checkered board. So 2, 3, 4, or 5 waves. And to get the result of the relaxation, for example, uh, if your point where you add one extra grain is, for example, here, you simply do 2 waves and you put there one more grain, and then it becomes 3. Okay. So what you can observe from these pictures is that those states, the result of sending some waves, are made in this example of the patterns, or all two horizontally or vertically, or all one diagonally. And those patterns are very special because they actually behave in a predictable manner under the action of the waves. They actually move towards the source of the wave. And therefore, for this reason, we call them solitons. And solitons exist for any rational slope. For example, you see this pattern 202, 202, 202 for the 1/2 slope. And the general theorem that I attempt to prove a little bit in the second talk, no, in the third talk, that those solitons exist and unique for every slope. Okay, and for your information, these solitons were coming under the name strings by the group of condensed matter physicists, Caracciolo, Spalletti, Sportiello. So the first work is in 2010, and this is actually how I myself was introduced to this through their work, then Nikita, then Ernesta, and then more people. So this is the origin, this Italian group of physicists who observed many things, but yeah, I'll tell what was our contribution in a few minutes. So in the second talk, waves and solitons, we discussed some of their definition, basic properties, and definitions, and the algorithm to generate a soliton of a given slope. Okay. And in the third talk, solitons and smoothings, we exactly prove this, that they exist via the procedure that is called the smoothing, that was called the smoothing. Now Nikita Kalinin calls it husking in his brand new paper on multidimensional solitons, which just got published. And in general, this was predicted by Sadhu and Thar, the stars of this field of sandpiles of self-organized criticality in 2012, that these piecewise linear functions should play a role in constructing solitons. And yeah. So that's our contribution. That's what we observed. Originally, it was that these pictures in sandpiles are actually scalable, and that there are scaling limits. So I think before us it wasn't observed. So, and we not only observed this, we proved it, and that's essentially to what is are dedicated the last 5 talks. To gently approach the formalism on the tropical side, because the limit is clearly something tropical, and to actually prove the things in 2 steps. So this proof of the scaling limit theorems is split in the 2 talks. One talk is the talk number 6, which is called Convergence Part 1, which proves partially, so not every details are covered, that for 1 point perturbation of the maximal stable state, that is all 3 states, there is some convergence results. So I don't state it today, so if you want, it's stated in this Convergence Part 1 talk. 3 versions of the scaling limit theorem relating the limiting shape to some very specific tropical curves and the polynomials that define them. Okay. So next, so the limit is defined in terms of omega tropical series. and I don't tell what it is. Well, I can tell it's quite simple. So at the base, it's like a piecewise linear function, only with integer slopes, such that it vanishes at the boundary of your domain. So this is an omega-tropical series. Also, it's supposed to be non-negative and convex. And we define a very special omega-tropical series, F omega, in the fifth talk, which is called the tropical caustic part 1. And we prove crucial property of this tropical curve for unimodular polygons in the fourth talk, which is called tropical caustic part 1. Okay, and what is the property? The property is that this curve is smooth except for a single edge where it's not smooth. So and all other points are smooth. And so that's the favorite example of this omega tropical series for a disk. And by the way, I wanted to mention that tropical series appear in works of Kisselman. And yeah, in the study, I think, of pluri-subharmonic functions. And this is the series, and this is how the curve looks like. So this is the caustic curve of the unit disk. And I love it so much, this shape. So makes me proud of what we did. And by the way, in these talks about tropical caustics, especially in the second one, we discuss some number theoretical, if you like, implications and toric geometry implications of this curve. So this second talk on tropical caustic is pretty eclectic and can be watched separately of everything else. But still, we needed to formulate the scaling limit theorems for the single point perturbation. So you can start directly from this talk number 5, if you like. Okay, and so this is precisely the relation of the sandpiles and to this curve. So if you take the disk as your domain and you intersect it with lattice with the small mesh, and you fill this domain with all threes, and in the middle you put 4, then that's what you get at the sandpile level, and you see that yeah, there is some convergence taking place, and this is the scaling limit theorem in its first form. Okay. So and yeah, I wanted to include these pictures. I like them also very much. This is how the caustic curves look for different squares. So for different squares in terms of this SL2Z. So those are different shapes because this is not the SO2, the rotation group, which is the main player at the tropical level. No, it's SL2Z, and those are different from the SL2Z perspective. Okay, and let's move forward. So many point perturbations. So when we add grains in many points, they give rise to the tropical sandpile model. And this is the subject of the seventh talk. And the first moment we realized this is a separate model that can be introduced, independently of sandpiles. I think this was a contribution by Ernesto de Perseu, who proposed that we study numerically this tropical sandpile. And maybe Nikita also was one of the guys who contributed a lot but there were several people, so I don't enter to that. So anyway, so this is one of our very popular work, self-organized criticality for the length of tropical geometry, where we show that this tropical sandpile model actually exhibits SOC, self-organized criticality, and it's the only known model which is also continuous and has this property. And like I had one extra thing that I think is very important is that it's SL2Z invariant. Okay, just to give you one flavor of how it looks like, this model is locally made of grain operators, GP operators. And you can see the picture of how it acts. So you take this thing on the left, which is represented either by the plot of the series, which is actually a polynomial in this case, a curve, and the point outside of the curve. And the operator GP shrinks the face of the curve, and you see the result of on the right. And these operators, they appear under the name breathing mode in Kumrun Wafa's work, so in the context of string theory. So before tropical geometry. Or am I wrong? No, I think I'm wrong. I don't remember which year is it, actually. Okay, I should have prepared better. Anyway, so I think the work is called something like supersymmetric partition functions and 4D string theory, something like that. Uh, so so anyway, so we use this tropical sandpile model to formulate and prove the many-point perturbation version of the scaling limit theorem in the 8-stock convergence particle. And that's it. So I was planning to make it short so that before diving into the whole series, you could watch this short video and decide if you like it or not. And, yeah, so I stopped recording. Thank you so much, and I hope you enjoy.